Assalamualaikum warahmatullahi wabarakatuh. So this is our last lab, lab number 14, the analysis of fluid flow and level control. First of all, let me introduce our group. My name is Muhammad Ikhwan, followed by Aina Nur Shahira, Juliana, Azri, and Muhammad Shahmim. And this is the Mechanical Engineering Lab, EMM 3814. Alright, next slide. First of all, let us introduce to you the objective of the experiment. So this experiment purposely is to determine the fluid flow using the PID controller. It is also aimed to study the effect parameter of proportional, integral, and derivative component value to the fluid flow and level control. Next slide. So the introduction of the overview of this experiment is a PID controller is a device that controls temperature, flow, pressure, speed, and other process variable in manufacturing control application. So the PID controller are the most accurate and reliable controllers because they operate a control loop feedback mechanism to control process variable. So it is commonly used in pneumatic and has evolved to include electronic and control. So the PID algorithm include three primary coefficients that indicate the PID, which is the proportional, integral, and derivative response that transform to achieve the best result for each parameter. So the performance of a controller system is typically assessed by using a stage function as the step point command variable and the observing the process variable response. So typically the response is assessed by analyzing specific waveform features. So a loop cycle is also an essential parameter of a closed loop system. So the interval of time between calls to a control algorithm is referred to as the loop cycle time. So in this experiment, the determining the best gain for PID and PID to obtain a precise response from a control system is called turning. So the turning method used in this experiment is the trial and error method to find the best parameter for the setting. We then proceed to the apparatus.
Aina, we cannot hear you.
Hello.
Okay,
Hello. Can you hear me?
okay, now we can.
Okay, sorry for that. There was a bit something wrong with the connection. So the apparatus used for the experiment was the SM514 PC level flow control, and we also have a personal computer that is used to run the DAQ software that is used to generate the flow control graph. The next one will be the experimental procedure. Shamim, can you uh, go to, okay. Um, okay. For this experiment, we will start with, first we have to make sure that the drain valve is discharged and the flow is set to 0. Then from the software, we will have to input the PID parameters of proportional, integral, and derivative, and click on the start button to run the software. And then the drain valve will set to auto mode, and we will have to switch on the button at the side of the equipment. And the flow control graph will appear in the software after a short while. And okay, the experiment is repeated by keeping the P and I value constant, and sorry, the P and D value constant, and varying the I values. Like that is all for me. Thank you.
So thank you, Aina Nushaira. So I will proceed to the result and analysis. Okay. The table below show the PID value for the three same experiment with different value of the heat integral times and other parameters remain constant. The heat proportional bands at the constant which is 15, and heating duration time also constant at 3, while heating integral time have different value which is 5, 7 and 9. Next slide. Okay. The first graph shown the line graph of the value of TK4 against time for the first experiment, and the value for the integral time is 5. So based on the graph, the blue line remain constant at 0 for 100 seconds after the experiment begin. After that, the value of TK4, the blue line, start to increase until it reach the set value, the pink color, which is 7. The time taken for the value of TK4, the blue line, to reach the set value, the pink line, is 90 seconds. After that, the value of TK4 reach. After that, the value TK4 reach the value of 7. The value of TK4 start to fluctuate between the value of 6 and 7. The fluctuation of the graph remain constant until the end of experiment, or the experiment is stopped. Next. So, okay. So this is the graph for the second experiment, which the integral value is 7. So based on the graph, the blue color remain constant at 0 value of TK4 for 15 seconds after the experiment begin. After that, the value of TK4, the blue color, start to increase until it reach the set value, the pink one, which is 7. The time taken for the value of TK4 to reach the set value is 85 seconds. After the value of TK4 reach the value of 7, the value of TK4 start to fluctuate between the value of 6 and 7. The fluctuation of graph remain constant until the experiment stop. Next. Okay, lastly, this is the third experiment where the integral time is 9. So based on the graph, the blue color remain constant for 15 seconds. For 30 seconds after experiment begin. After that, the value of TK for the blue line start to increase until it reach the set value, which is 7. The time taken for the value of TK4 to reach the set value is 85 seconds. After the value of TK4 reach the set value, the value of TK4, the blue color, start to fluctuate between the value of 6 and 7. The fluctuation of the graph remain constant until the experiment stop. That's all for the result analysis. I will pass to the Shami.
Thank you, Azri. So as for the discussion, the first thing that we're going to discuss is um, uh, observe or analyze the trial and error method as to find the best way to approach this technique. So first, we are going to set all the gains to 0, and then we increase the proportional gain until the system oscillates. Next, we increase the integral term until the steady state error is minimized. But in this step, the overshoot the overshoot behavior may increase. Therefore, we increase the derivative gain to reduce the overshooting. But as for the consequences, it may slow down the response. So for the other alternative method, besides try and error to tune the PID, is the Ziegler-Nichols method. So this method has higher accuracy compared to try and error method, and it requires the oscillation period to be identified beforehand. Next, we're going to discuss is the influence of item in the PID controller, as we are only manipulating the value of the integral. So I stands for integral, and it uses the technique of capturing the value of processes variable over time, and mostly used to eliminate the system's steady state inaccuracy. And for example, when the system is reaching the targeted magnitude, the signal would try to oscillate, and this produce a steady state error, like a sinusoidal wave. And the integral parameter is responsible for providing corrections to the signal in terms of minimizing or even eliminating the steady state error. So the errors that we encountered in these experiments, the first one is the poor PID tuning, which is causing the performance retardation to the system. And the next one is the software breakdown, which lead to computer reboot. So the second one, we cannot really do anything other than restarting the computer. So as for the conclusion, I will lend to Anna to proceed.
Okay, so thank you, Shamim. So I'll continue for the conclusion of this experiment. So the experiments will determine for the experiment helps to determine the fluid flow using the PID. The fluid flow and level control system can be maintained and managed by the integrative achievement goals. The control components, which is the PID controller, can ensure that the equipment performs at its best by preventing and minimizing control system errors. So I think that's all for the conclusion. So thank you. So that's all for the lab 14 from our group. Thank you.
Thank you, Doctor.